Hello. We were deriving an expression for the entropy of the classical ideal gas system from the calculation of its multiplicity. So let us continue with the derivation. So in the last session, we obtained an expression for the omega. So let me just show you the previous slide. Yeah. So equation number 5 was giving you an expression for the multiplicity omega of the given system, and we can calculate the entropy of the system by using the famous Boltzmann's relation for entropy S equal to K log omega. So let me make the substitution here. So I have to substitute for log omega, and then thereafter we can multiply with the Boltzmann constant to get the entropy. So let me calculate log omega first. Okay. So what is log omega? Therefore log omega, I'm separately calculating log omega. Okay, of course you can keep the K also, so that will be equal to, see, I have take log of equation number 5, RHS of equation number 5. So can you see that here I'm treating, I'm treating, let me just show it like this. I'm treating this many things as, say, numerator, and this thing as denominator. Okay, so now this is of the form something like a by b. Okay, omega equal to a by b. So if omega equal to a by b, what will be log omega equal to? Can't you write it as log a minus log b? Okay, so I'm going to write like that. So I'm writing log omega is equal to log a, means log of the numerator, and you can see that that a is just with a power en. Somewhere there is a power, common power en here. So here is n power, here also there is a power en. So I'm taking, log of this one will be equal to n log a minus log b. Okay, so I'm writing this one as simply like this, n log. After my writing, I think you will understand it better, n log. So the remaining terms, okay, what will be the thing? See, already this n has been taken, so it will be v by h cubed. Just cross check it, v by h cubed, right? Then from here also 2 pi me term has to be taken, but this n is taken. So what is remaining there? 2 pi me raised to 3 by 2 into 2 pi me raised to 3 by 2. So this much terms are remaining there. So that is my okay, numerator is taken. So now denominator is 3n by 2 factorial. So minus log a minus log b, log of minus log of, be careful when you write it, use proper number of brackets, 3n by 2, the entire thing factorial. So log of that thing. So this, let me call this one as some equation number 7 or something like that. Okay, now you got something of this kind. What we can do, there is a mathematical identity known as Stirling's formula. Okay, Stirling's formula. I'm reproducing the Stirling's formula here. We are borrowing this particular equation. Okay, once again. So by Stirling's formula, you can refer to Stirling's formula. Many of the mathematical physics books as well as statistical mechanics books will be giving you Stirling's formula and its derivation and its proof as well. Okay, just you can check it. It will be given as some appendix in many of the books. By Stirling's formula, that is a formula that repeatedly being used by the principles of statistical mechanics. Okay, log of n factorial, log of some n factorial will be, or it can be written approximately as, so I'm writing approximately as, log n factorial can be expanded approximately as n log n minus n, n log n minus n, and this approximation holds good when this n here is very large, for large value of n. So this particular formula is an approximation, of course, but this approximation will not lose, will not take away any, what is that, considerable accuracy. Okay, n log n factorial can be taken as n log n minus n. So this is a valid approximation for very large value of n. So what is the use of this Stirling approximation in our present context? We can see that in equation number 7, you have got the second term, log of z, log of, if you consider this one as some small n in our, okay, n here, log n factorial. So in place of small n here, we have got some 3n by 2 factorial. Okay, 3n by 2. So that this is log n factorial form. And don't you know that, okay, you know, the condition is holding good in our case. Why? Because you know, we have been telling that the n that appears in this 3n by 2 is nothing but the number of particles of our thermodynamic system, which is of course of the order of what Avogadro number, because we are considering some gaseous molecules or some other thing. Okay, thermodynamically, you know that this n number of particles are pretty large, and that is what we say that n is tending to infinity, or we consider the properties of systems which are in the thermodynamic limit. Hope you remember that why did we discuss about the concept of thermodynamic limit in the very beginning of our discussions. The reason is that in the thermodynamic limit, we can use such useful approximations like Stirling's formula, okay, which can be applied only for large values of n, and our assumption is well suited to use is Stirling's approximation. So simply what you can do is that you can apply Stirling's formula for the second term, and let's rewrite equation number 7. Let's rewrite equation number 7 suitably. So let's see how to rewrite that one. So I'm just going on. So our aim is to calculate the entropy of the classical ideal gas. So I'm rewriting equation number 7 this way. So log omega, it's better that you go on writing it, okay, so that no. Now so far I have been writing equal to. Now I just make an approximation that it is roughly equal to, but this approximation doesn't affect us. So the first term I am retaining as such. So log n log, then whatever thing was there, v by h cubed. It's good that you repeatedly write it, okay, until you become familiar with the terminologies and the symbols used. 2 pi me, okay, raised to 3 by 2. Was not our first term, raised to 3 by 2, minus the second term. I'm applying what? The Stirling's formula. So what should be the second term? It should be log n factorial. So this is your en, okay, log n factorial. 3n by 2 is your n. So that should be equal to n log n minus n. So let me open up n equal to 3n by 2. So I'm just writing it straightforward. So minus 3n by 2, n log n. So it is n is 3n by 2 log 3n by 2. See, log of 3n by 2. See that, okay? I'm not putting brackets. You can understand that. Log of 3n by 2. N log, yeah. You can write it like this if you want. So n log n minus n. So there is a minus, but already there's a minus here. So the last term will be plus, right? So it will be plus 3n by 2. So that is going to be our equation after applying Stirling's approximation. Now what I'm doing, I'm just making some more modifications. So that's again roughly equal to, I'm retaining the first term as such, n log, our aim is to just simplify this equation to some reduced form. So v by h cubed 2 pi me, all those things are keeping as such. So 3 by 2. So the first term I haven't touched at all, minus, but second term I am just making some modification. What I'm doing is that I'm taking this 3 by 2. 3 by 2 from here, I'm taking it to, okay, so you can understand from my writing, n log, I can write as a power, n log 3n by 2, the power 3 by 2. Okay, and maybe you will see shortly what is the benefit of this particular step. We have some motivation. Okay, so I have taken this 3 by 2 from here and I have expressed as the power of that logarithm. So that is, of course, you can use log a raised to n is equal to n log a, or whatever it is, okay, the form that you can follow. Now, what is the advantage is that I can combine now. You can see that the first term here is n log something, n log of a, and second term is minus n log of something, so that is n log b. So n is common. So I can take n as common out of first and second term. So n, then that is of the form log a minus log b, that is log a by b, right? So I can write this n log, first and second terms I am combining, okay? Then v by h cubed, it's a bit lengthy but doesn't matter, okay? Then it will be, how it will come? So divided by, right? So v by h cubed, 2 pi me, you can see that, so there are several terms that are common, okay, raised to 3 by 2 divided by, so that is a minus b, so a by b. So what is that? 3n by 2 raised to 3 by 2. So divided by 3n by 2, 3n by 2 raised to 3 by 2. Can't you see that this particular both of them are having what? raised to 3 by 2, okay, common. So plus what is remaining, this only term is remaining now, that is 3n by 2. Okay, so that is again equal to, I'm just rewriting it as n log, you know, we can make one more okay, just reduction. So that is this 2, both are having 3 by 2 as the power, so I can combine it without any trouble. So this 2 in the denominator goes to the numerator, so 2 into 2 become 4, so that becomes finally 4 pi me by 3n. This is an equation that is worth remembering, okay, so that you can cross check it once you derive it, you do not miss out anything. So whole raised to 3 by 2 plus what, 3n by 2. So that is may say maybe some equation number 8 or something like that, whatever it is. Yeah, equation number 8. Okay, Stelling equation I'm not numbering, that's equation number 8. So that you got log omega by the time, right? Therefore, of course, you can use the previous equation, entropy. Therefore, entropy yes is equal to simply k log of omega, that already we are used. So that will be equal to, finally what's that? That's equal to, let me write it. That's equal to simply k into n. So I'm writing for some symmetry nk or kn also, nk log. This is a standard expression that will be finding in many, okay, what is say that many of your StatMech textbooks. V by h cubed, no other changes elsewhere, 4 pi me by 3n, 4 pi me by 3n, whole raised to 3 by 2, whole raised to 3 by 2 plus what? I'm multiplying with the k both the terms, so it would be 3 by 2, I can write now like 3 by 2 nk, 3 by 2 nk, s equal to, right? So that is our equation number 9. Okay, and see that this is a one see very special equation, so I just box it for the time being. So this is the one what do you say that very relevant result that we have obtained by using statistical methods. Okay, so you can just see that why this equation is relevant. You can see that finally we have been successful in obtaining s as a function of what? Its macroscopic variables or macro state of the given system, that is NVE. And we have seen from the recipe that if we are able to obtain s as a function of NV and E, the natural variables or the macro state variables of an isolated system, you can obtain all other thermodynamic properties starting from this s by taking partial derivatives, which we'll be doing. So this gives you the expression for the entropy of a classical ideal gas derived statistically from the multiplicity. And see, this is usually known as the classical expression for the entropy, but I think it's many are having the opinion that this one should be regarded better as a semi-classical expression. Semi-classical expression for okay, that will be justified. Okay, semi-classical expression for entropy. Why don't I? Okay, or why don't we call it as the classical expression? It is being used as classical expression, but I think it's better to regard this one as a semi-classical expression. Why it is semi? Because you know that our ideas are not purely classical. In between, we have used in the counting of omega, we have used what? That is equal to VQP divided by h raised to 3n. And where come this h, Planck's constant, and h raised to 3n, the minimum phase space volume came, that you know that came from the uncertainty principle, which was an idea that was shared by what the quantum mechanical consideration. So we can say that it's partially classical concept and partially what? Quantum concept. Okay, because we used phase space, which was a classical idea, and we used the uncertainty principle, which is a quantum idea. So we can say that equation number 9, which is our ultimate equation for the entropy of classical ideal gas system, it can be regarded as a semi-classical expression for the entropy of the system. Doesn't matter whatever way you get it. Okay, it has undergone a number of revisions. See, this is what we do. Remember, there are many other steps or many other methods by which you can reach the same equation. I just followed something that is logically easy to understand. You can have any other equivalent derivation that is given in some other textbooks or some other help books. We can follow that. There is a slightly different derivation given in Petria. I have followed a part of that one, a part of from somewhere else. What is logically easy to convey, and easy to teach. For pedagogical purpose, I found that this particular concept is useful, by counting it, by considering the total phase space volume and dividing by this concept. This concept is found to be pedagogically easy to convey. That's why I followed this particular methodology. You can follow any other equivalent methodology. If you want, I can give some lecture notes on that one also. I can share it with you later. But whatever you are doing, see that you are thorough with what we are doing and why we do. That should be thorough with to the maximum. So that is the entropy. Now, before I end up this session, quickly we can go to the thermodynamics of the classical ideal gas system as a continuation of this lecture, starting from equation number 9. It's quite easy. Just you have to take a couple of partial derivatives, which we can do within no time. So let's go to the thermodynamics of the system. So derivation of the thermodynamics of the classical ideal gas. It's a continuation of the same discussion, classical ideal gas. So how do we begin with? So see that we have equation number 9 of entropy with us, and I just use we have. So let me use the the first law of thermodynamics in its differential form, that is dE equal to, or du equal to, dE equal to, what is the equation for any closed system, that is TdS minus PdV. We will be depending on this equation frequently, plus mu dN. So that we can refer to. So let me say that this is my equation number 10. Now from that, can you get, therefore dou S by, we will be taking one by one. Let me take dou S by dou V. Dou S by dou V first. Dou S by dou V. Keeping, you know that of course E and N should be kept a constant. E and N should be kept a constant. I'm taking dou S with the dou V, right? If you want, you can just take the other way also, right? Or let me write this equation in the other way. What is that? ds is equal to, the same equation can returns, ds is equal to what? dE by T plus P, better that is P by T dV, minus what will be that? Of course, mu by, right? So what I'm doing is correct, I think. Yes, yes. So what I'm doing is I write ds is equal to, of course I'm taking all other terms to the, so it is a mu by T dN. So better, let me call this one as equation number 10. So that's always good. Otherwise, so I started from there and then I just change it. So let me say that this is equation number 10. So now it's not easy. So otherwise also it's okay. So dou S by dou V. When you take dou V, I'm keeping dE and dN 0. So means E and N should be equal. So what do you get? Dou S by dou V will be equal to 1 by T. That will be equal to 1 by T. Is it not correct? So no. So dou S by dou V, by dou V. So it should be equal to P by T. It will be equal to P by T. So we use small p here. P by T. So this term will be there because other two terms are 0. So that is equal to P by T. So we say that this is equation number 12 or 11. Equation number 11, right? And what you have to do is that, can't you take dou S by dou V from our semi-classical expression for entropy? What is that? This is your S. So let me take that S for reference. Let me take that S here to the next page so that you can refer to it. Just a moment. I'm making some arrangements here. So I'm keeping it here as a reference. Here it is. This is for our reference. So that was our equation number 9, right? So what you can do is that, so from 9 is this one. So this is your equation number 9. What will be dou S by dou V? Let's take the partial derivative. Dou S by dou V, keeping what and what? E and N constant. So same thing we are calculating from 9. What will be that one? Equal to, that is equal to, see, I have to take the derivative of this s with respect to what v. V is the variable. So where come v? Where all v terms are coming? V term is coming only in this particular term. So this term will partial derivative with this will remain as a constant because n is kept as a constant. So this will vanish. So it will be simply nk into log of this particular thing. So log of v, what will be the thing? So I'm just doing it for you. Derivative of log, it will be equal to 1 by, log x is 1 by x. So you have to use function rule. So nk are constants. I take it outside the derivative. So nk into dou by dou v of that equation. So I'm writing it like this. Nk into, you can check it, 1 by that entire thing. Whatever is taken as x, you call this one as x. 1 by, so v by h cubed. See that you write everything into 4 pi me by 3n whole raised to 3 by 2. That is that into, so by function rule we are taking 1 by x into see derivative of this quantity, derivative of this one with respect to, so that v will be gone. So what will be that one? That is equal to 1 by h cubed into 1 by h cubed, the remaining thing 4 pi me raised to 3 by 2 by 3n, of course, that this 3 by 2 is applicable for 3n also. So what will happen is that this h cube will be getting cancelled, 4 pi me will be getting raised to 3 by 2 will be getting cancelled. So what is remaining is only, what is remaining here? So that gives only nk by v. So that is my equation number 12. Can you see that equation number 11 and 12 has got the LHS as same, dou s by dou v. So you can equate RHS of 11 and 12. So from 11 and 12, what do you get? You get P by T is equal to nk by v. Or can you just cross multiply it? Cross multiplying, what do you get? You get PV, I'm cross multiplying PV equal to what? nkt. Don't you recognize this particular equation? And I think we should be all, or we all must be happy for some reason. Why? This is nothing but the familiar ideal gas equation, which is nothing but the ideal gas equation that we have started our discussion with. And can you see that something wonderful that has happened? We went through a technique or a method which was entirely different, which has nothing to do with what? Thermodynamics. We went through some statistical principles by calculating number of microstates, omega, phase space volume, and then we obtained a semi-classical expression for the entropy, and from that entropy, by following the recipe that we have discussed, we are able to derive the the hallmark equation of classical ideal gas, PV equal to nkt. So this is quite a success of our methodology, what we are following now. So that is why I told you in the beginning of our previous discussion that we are using classical ideal gas as a testing system. Once we are able to arrive at the ideal gas equation by following the newly introduced method of statistical multiplicity, counting of microstates, we can make sure that our method works, our system works. So we can say that our ideas, or our idea means, we identify with Boltzmann and Gibbs, that V means the physicist ideas of statistical mechanics is truly wonderful. PV equal to nkt. Of course, you can just rewrite this one as what I told you, that this k is equal to, what is that? This k is equal to nothing but kb is x plus r by na, the ratio of two other fundamental constants. So you can just write what this is n, into kb is r by na. Wherever needed, you can just rewrite that r by na into t. And what you can do is that you can write this one as n by na. N is the total number of particles in the sample system into RT, and total number of particles divided by Avogadro number will give you the number of moles. So that will be becoming finally nRT. So that is yet another form of what? The ideal gas equation, right? So hence gives the equation of state. We call it as equation of state of the classical ideal gas. So this is actually a point of celebration for statistical mechanics, okay, because we are able to get something that was that is well known to us by going through very, what you can say that okay, very unfamiliar terms through entirely different just path, the path that is not that much traveled, but finally we are able to get something very quite familiar equation. Okay, that's of course a moment to be celebrated, right? Actually I should stop it here, but see the time constraints force me to take one more step, because we are deriving the thermodynamics. It's not enough that you get the equation of state. We have to get what, two things more. Similarly, so I just proceed. So let me take this S equation with me. That's better, because the equation we need it. So let me take it to the next slide 2. We are continuing with the derivation. So this is S. This is for reference. I am keeping this equation here. So let me once again, yeah. So now we are taken only one partial derivative. So you know that this S is written as a function of NVE, right? So we are taken the partial derivative of S with V. Similarly, you can take what the partial derivative of S with E, right? With E also. So let's see how to do that. So also, to begin, also dou S by dou E, dou S by dou E, right? Dou S by dou E, keeping what and what? N and V as constant. So what will be dou S by dou V? Keep dou E keeping N and V constant. So from this equation, dou S by dou E, okay, means keeping N and V constant means this term and this term will be vanishing. So it will be equal to 1 by T. That will be equal to 1 by T. It's equal to 1 by T from equation number, what is say, what is the equation number that we are given? Please, equation number 10. From equation number 10. From 10. So let me call this one some other continuous equation number. Let's give equation number some 13. Equation 30. So I'm calling this one equation number 30. And you can get dou S by dou V NV from this equation number 9 also. From 9, let me write dou S by dou E, okay, NV, the same quantity I'm evaluating, that would be equal to, see, I have to okay, take the partial derivative with respect to E, partial derivative with respect to E. So means with respect to this quantity. So E appears only in the first term. So the partial derivative of the second term will be vanishing. So we are left with this one. Same format that we are done. It is nk is taken outside. Then log of something x. You call this entire bracket as x. So it will be equal to 1 by x into then function rule. So you have to take v by h cube, then e raised to 3 by 2 is there. So it will be 3 by 2 e raised to 1 by 2. Okay. So I'm just writing it for you here, so that we nk is taken out. So nk is there. Then into 1 by x, log of x is 1 by x. So 1 by the entire thing, v by h cube, the entire thing in the bracket. So v by h cube 4 pi me divided by 3n whole raised to 3 by 2. So entire thing in the bracket into, what do you do? So then I have to take the derivative of this particular thing, right? So that will be equal to what? See, v by h cubed, that's taken as a constant, v by h cubed, keeping apart that e, 4 pi m by 3n raised to 3 by 2. So I have kept that e separately outside, because all these things can be taken as a constant. Then see, e raised to 3 by 2 is there. So what will be the derivative of e raised to 3 by 2? That should be equal to 3 by 2 e raised to 1 by 2. So into 3 by 2 e raised to 1 by 2. Please check it by yourself. Just you can do the partial derivatives. Simple differentiation only. So what happens is that here everything else, okay, other than this e raised to 3 by 2 will be getting cancelled away. So this particular thing will be remaining. So I'm just retaining it. You can keep that one as separate. Okay, so there is e raised to 3 by 2 in the denominator. There is e raised to 3 by 2 in the denominator. There is e raised to 1 by 2 in the numerator. Right? What will happen? 1 e raised to 1 e will be in the denominator. So I'm multiplying, I'm cutting this one with this one. So what remains is there e raised to 1. Okay, e raised to 2 by 2 is there. E raised to 2 by 2 is e raised to 1. So e raised to 1 remains. This 3 by 2 remains. This okay, nk remains. So what all things are remaining? I'm putting it together. So that is equal to, what is equal to 3 by 2 of course is there from here, right? Then this nk is there by e is there. Nk by e is there, right? So that we call this one as equation number some 14. Now can you combine 13 and 14? So 13 and 14 can be combined because LHS are equal, so RHS should be equal. So what I can write? So I can write 1 by t is equal to 3 by 2 nk by e. Can you rearrange to get what is E? E is the internal energy. Okay, total energy is purely internal kinetic energy, that is internal energy of the classical ideal gas. So E equal to, on cross multiplying, you will be getting it is equal to 3 by 2 nkt. 3 by 2 nkt. And you know this nk can be substituted with what? Nr by using previous discussion. Okay, so which is equal to 3 by 2 n small n r t. And this is another familiar expression. The familiar expression, familiar equation for energy, means internal energy of classical ideal gas. Familiar from where? From our kinetic theory of gases or from the thermodynamical considerations. This was equation that we have already obtained. So once again a success for our principles, telling that this equation should be okay, no, it should be we cannot confirm that this equation is completely correct. Okay, so because there are usually, you know, that in mathematics something may be correct, so we prove that this equation is having a chance to be correct. We cannot celebrate completely. Okay, so that's a word of caution that I keep you I give you beforehand. So just because that we are able to derive two results which is familiar to us, we cannot say that this is completely correct. Okay, I will tell you the reason later. Okay, this equation need not be completely correct. There can be some pitfalls for this equation, but okay, there is enough for a celebration. Okay, part of the celebration here, that's there. Now, so we got two of the famous equations of state. Okay, internal energy we got the expression internal energy. Now let's derive see two more things. Let's get the heat capacities. Okay, you can derive any quantities actually, depending on if you want, you can just derive mu by taking dou s by dou n, but let me derive the main quantities here. So let me derive now. So these are the quantities that is relevant. CV. What is CV? I think you remember that in the recipe we have discussed CV is nothing but the derivative of internal energy of the system with respect to temperature, keeping V and N constant. Okay, since it is CV, it is V. Just recall the recipe. Dou U by dou T or dou E by dou T, keeping V and N as constant. So that is quite simple. Why? You have got E. What is E is equal to? E is equal to 3 by 2 in terms of temperature. We have got either 3 by 2 nkt, which is also equal to 3 by 2 nRT. Both the ways you can write. So I have to take what? Just simply dou by dou T of the first term, that is 3 by 2 nkt. And can you say that's quite simple because n is kept as a constant here in taking the partial derivative. So I can take 3 by 2 nk as a constant, and dou by dou T of T is 1. So it is simply equal to 3 by 2 nk, and nk can be written as what? Nr. So which is also equal to 3 by 2 nr. That gives you the CV, heat capacity at constant volume for the classical ideal gas system. Similarly, do you remember what is Cp equal to? We proved that Cp is equal to dou H, the enthalpy, dou H by dou T. Cv equal to dou E by dou T, and the other one Cp equal to dou H by dou T, keeping, so since P is kept a constant, we have to keep P as a constant, and N is also kept a constant. Okay, P and N as a constant. So that is equal to, let's see how to do that. That is dou by dou T of, what is H equal to? H equal to U plus PV. That is the Legendre equation, right? Legendre transformation relation. H equal to U plus PV. Instead of U, we are using E here. E is the internal energy. So E plus PV, okay, keeping P and N as constant. That's the idea. So which is further equal to dou by dou T of, let us rewrite. What is E? E is equal to 3 by 2 nRT. E is equal to 3 by 2 NKT or nRT. So I'm using one of them. There is no problem because by with respect to temperature, 3 by 2 nRT plus. And don't you know, since we have established what is PV, PV already we have established that is equal to nRT. So I can write for the second term PV, I'm writing nRT. So I'm writing nRT for the second term. So I will be getting finally this is equal to 3 by 2 nRT plus nRT is what? Finally 5 by 2 nRT. 5 by 2 nRT. Okay. Or see you take you have to take this one okay dou by dou t of okay, that's a mistake from me. Dou by dou t of 5 by 2 nRT, 5 by 2 nRT, and so 5 by 2 nr is taken out, and that t that's gone. So finally in this expression there won't be any t here. So that is finally you are getting what's equal to 5 by 2 nr, and nr is equal to nk, or you can write as 5 by 2 nk also. Both are equation. So we said that this is equation number some 14, whatever it is, okay, some continuous numbers. This is what, some 15. Now you got CP and CV. Once you get CP and CV, can you find out? So can you just verify CP? Therefore clearly CP minus CV. What is CP minus CV equal to? You can see that CP minus CV will be equal to 5 by 2 okay nr minus 3 by 2 nr. So how much is remaining? That is equal to nr. That is equal to nr, right? Okay. Or for n equal to 1 mole, when n equal to 1, when n equal to 1, we call that CP and CV as what? Molar specific capacity, is it not? Or specific capacity, okay, molar value. When n equal to 1, you will get it as what? Molar specific capacity. So you will be getting CP minus CV is equal to 1. Then instead of capital C and capital C, we can use small c as well for molar specific capacities. That will be equal to simply R. And I think you are familiar with this equation. This is a famous what? Mayer's relationship in classical ideal gas. Mayer's relation. All these are thermodynamically proven okay relationships, which we are reinventing by following an entirely different approach of statistical mechanics by counting microstates. Moreover, let's anyway we have come this much. Can you calculate the ratio of specific heats gamma? Gamma is equal to CP by CV, you know, that is equal to 5 by 2 nr divided by what? 3 by 2 nr. Okay, just work it out of okay, no, see, so getting cancelled, so 2 and 2 getting cancelled, so it will be equal to what? 5 by 3. Okay, 5 by 3, and you know gamma equal to 5 by 3, it means that what? Gamma for what type of system gamma equal to 5 by 3? Gamma equal to 5 by 3, you know that it's for monoatomic gas. And in our very assumption of kinetic theory of gases, we were considering every molecule to be ball-like, point-like. Point-like means we neglect the diatomic structure and all. Means what? Monoatomic, because we know that that is classical ideal gas is gas is monoatomic. That is our assumption. It's all spherical in shape, so it is monoatomic. Okay, we neglect its extended sizes. So I hope that you follow what I am trying to convey you. Okay, so I have tried my level best. Please keep on reading the concepts so that you get a better idea of what I am doing. Okay, so that's about the classical ideal gas as mentioned in your syllabus. Thank you.